Okay, hello everyone. Welcome again to the review session for um, Shaliji's textbook. We'll be covering the first three chapters today, and I'll be moving sort of quickly. So please take the initiative to make me stop and re explain things if I'm going through something really quickly. We have about an hour and a half or an hour and 20 minutes. My bad. Almost 2 hours. And I'll take a couple of breaks in the middle so that you can ask questions, relax, drink a glass of water, coffee, what have you. So last time in the overview, I told you that the first chapter was more about breaking down the different pieces involved in performing regression. But before that, stepping back and like looking at why do we need a regression? What are these models? What are these assumptions we make? Like, why do we care about finding patterns and how do we find patterns in data? And we stepped one step further back and looked at all of this high level motivation of why statistics is useful, what it gives us, and like why do we do all of this. So I'll start from there. And the general idea is that statistics is the analysis of data. Data tells us about various processes in life, from science to technology. All of our analysis usually comes from performing experiments, obtaining data, and then analyzing the data about those experiments. So what we do is we handle, and our data is not perfect. In a lot of cases, the data that you collect will have some inherent noise, whether that is the noise due to the imperfect measure. Typically, that noise is due to the imperfect measurement of the process itself. So what we do is we say, okay, we start creating an assumption of this random process, and we draw some data from that random process, and we say, okay, if we create a world that is similar to the real world, then hopefully what analyses we do on this world will map to the real world. And that is the underlying motivation for all statistical modeling, that okay, if we can create a realistic enough picture on paper, then that picture will translate well into real life. And to some extent, for all of you machine learning folks out there, this translates into all of your generalization. So how well can this model generalize? Like, okay, great, it works well on the training data, but how well does it generalize? And that generalization relies on your assumptions about the training set holding true for your test set and in the real world. So the first two chapters go into detail on all of those assumptions that you make. Even simply saying this linear model works for this data means you assume 10 different things about that data. Whether where the data came from, what was the noise structure in that data, are all of your samples independent and identically distributed? Is there a linear, non-linear relationship between your x's and your y's? And we'll get into all of that in mathematical detail. And it's nice that the textbook does that from first principles, because a lot of times we skip over things, particularly in machine learning. We care about prediction, we don't care about interpretation a lot of times. So if we get good predictions, we tend to say, oh, I did well, and you actually haven't. So, and that is sort of the motivation for this whole let's keep a training set and let's keep a test set and not use the test set to train our data, and then use the test set to evaluate these models. And the underlying assumption there is that these data are well representative of how the real world looks. If they're not, then you can't do anything. If your data are bad, then your model will be much worse. But if your data are good, your model can be okay. No model is perfect. That is an informal law of statistics. If you're ever finding a model that perfectly fits the data, then you're probably overfitting and you're going to generalize very poorly. So, yeah, with that in mind, let's start with the first chapter. Um, One of the things that people want to know about the world when you are given some data is how the different variables relate to each other. And one of the central tools statistics has for learning about these relationships is regression. And this textbook assumes a bit about linear regression, but we won't do that. And I'll get into the details wherever possible to help you understand what I'm talking about from the ground up. Okay. So, linear regression is just one member of a big family of smoothing methods. And what do we mean by smoothing methods? We just mean like if you have some data, smoothing just means you're connecting these with a particular line, curve, whatever. And as opposed to this point wise data, you're now getting a continuous data in a sense. That's called smoothing. And there are different kinds of smoothers. For instance, this is one smoother that I drew. Another one I can draw is like this. Doesn't pass through all of the data, but it's a linear model and it fits the data to the best of its abilities. Or it may not even fit the data well. I can draw something like this, and it's still one model for this data. And it's not a great model, but it's still a model. So how do we pick, like, what do we do to get a good model for the data? Well, we formulate a problem around this which says, okay, I want to now minimize the error in prediction with this model and this data set. And how do I do that? Well, I formulate this error called the mean squared error, that allows me to guess the value of a random variable. And to be clear, this data comes from a random variable. A random variable is taking all of these values and we're fitting a model to that data. Um, yeah, I don't want to say anything more about it. I think I gave you a summary of what a random variable is, what distributions are. If that's unclear, interrupt me now and ask me a question. Okay, seeing none, I'll move forward. A random variable is just the outcome of a random experiment. A distribution is um, probability um, of each value that it takes, um, plotted on a curve, plotted on a graph. So yeah, random variables, distributions. Some two important concepts: expectation and variance. Now what happens is when we have two different random variables, okay, they have their own distributions and we want to compare them. For example, if we fit two lines, how do we compare which line is a better, not a better fit to the data, but if I didn't have any data, I just have two lines and I want to say something about that comparison, what do I do? That's where it, you can't say that this line is takes the value 1 at x equal to 1, takes the value 5 at x equal to 4, takes the value 7 at x equal to 3. That's, it's hard to explain to someone that that is the way the data is structured. So you want to create a summary of these distributions, and those are called summary statistics, the numbers that summarize these distributions. One of those is the expectation, the expected value, the average, um, weighted average of the data. what what I'm trying to get at is, this is also called the first moment of a distribution. And sometimes what happens is a distribution that looks something like uh, this may have the same first moment. So the mean of this distribution lies somewhere here. And a distribution that goes something like this may also have its mean lying somewhere here, but they're different. And if you use only the first moment, the expected value, then you're going to get the same value and you won't be able to compare the distributions. So then you go on to the second moment and you say, okay, now I'm going to evaluate the variance of the data. And by that variance, you will get that this bimodal distribution, bimodal means it has two peaks, is has a higher variance than this unimodal distribution in blue, which has just one peak. um and so it is a sense of the spread. In a sense, it is like what is the spread of your data, that is measured by the second moment or the variance. And you can imagine that these moments keep going on and you can find the kth moment. In fact, the third moment is called the skew, the fourth moment is called the kurtosis, and that's used in some mathematics that I'm unaware of. but the bottom line is you want to compare distributions, and at some point they will differ. In For this textbook, we typically just rely on mean and variance. So I wanted to give some intuition for why we care about those. Um, and yeah, so now we spoke about finding this optimal estimator. Um, and we use a loss. We minimize a particular loss in order to say that this blue line is worse than this green line. Um, so let's look at what this loss is. So this loss is saying, the first let's look at the problem setup, right? So we have some response variables y, we have some covariates or predictors x, and now we want to find some set of parameters beta, which when multiplied with the x gives us the best approximation to the y. And um, this beta is what we call our um, parameters. Um, but I already said that. Never mind. So our estimator is this line. This line is called an estimator for the true function. So we assume that there is some true function that passes through this data. For example, the true function might be something like this. And we want to estimate this true function using some method that minimizes some sense of a loss function. Um, or a loss function is too complicated to use here. So minimizes some sort of error, um, which fairly straightforward. Again, reminder to interrupt me if I'm spending too much time somewhere or too little time somewhere else. Um, we get into the proof of breaking down this mean squared error into bias and variance, and because this is done 3 other times in this chapter itself, I'll go into a bit of detail. So to give you some context, one of the laws of expectation is that expectation is a linear operator. So if you take the expected value of x plus y without any assumptions, this is equal to the expectation of x plus the expectation of y, which is why we say expectation is a linear operator. Okay. Now, using the same principles, what we do here, when you are saying what do you want to find, you want to find the expected value of this error term. So on average, what error am I going to face with my predictions? And then I want to say that if I minimize this error, man, I should, I'm going to make Shanai co-host just in case anyone shows up later. You can check if there is anyone in the waiting room. Okay. Anyway, getting back to what I was talking about. And then what we want to do is we want to later say, okay, I want to minimize my mean squared error, and I want to find the minimum m that does this, because y is fixed. So y doesn't change. For a given data set, your response is going to be fixed. All that's going to change is your m. So you want to find the m that minimizes MSE. Technically, it should be argmin m that minimizes the MSE, but okay. For now, we define the error and we break this out. How do we break this down? If you look at this blue stuff, what we do is we expand it out. We add and subtract this term, expected value of y. And why do we do this? We do this because that allows us this flexibility to then break this open into a plus b the whole square. So you have an a squared term. Sorry. You have an a squared term. You have an ab term. and then you have b squared term. And the nice thing about this, in case anyone notices, is that your AB term, the middle term, it should be 2AB. Your middle term tends to 0. And why is that? Because for your optimal predictor, mu, it's going to tend to the expectation of y. So as your predictor becomes perfect, um, your middle term tends to 0, which is explained here. Uh, Maybe I didn't explain that right. Um, Yikes. Hmm, I think that was okay. Well, in any case, what we really want to do is to take the derivative of the mean squared error with respect to this prediction and say that at the best prediction, this dy by dx will be 0. So your this goes back to your linear algebra where, not linear algebra, calculus, where if you want to find the minimum of a function, find dy by dx, set the minimum to 0. And by that definition, you will find this minima of x at dy by dx equal to 0, because the dy by dx represents the gradient. At this point, the gradient is 0, and that is the underlying assumption we have. Anyway, um, if there are doubts, again, please stop me and ask me.
Hello.
Yeah,
Yeah, so you earlier said that y would be fixed, but isn't y a random variable? And so,
you're
in
right.
what, so would it be fixed or it would fluctuate, or in what specific scenario would it be fixed?
That is a great point. Thank you for clarifying very much. So we're taking x and y as our random variables. What I meant was, given a data set, those x's and y's are fixed, but that's not what we're talking about here. Here we're talking about the random variables x and y. So excellent question. Thank you so much for pointing this out. What we are saying is, our guess, we'd like to find the optimal value mu, where this mean squared error, so mu is this optimal point forecast, mu is fixed, and we don't know what mu is, we want to find the mu. We start by picking guesses for m, and we want to find the point at which this m is the closest approximation to y. So, and a very easy way to figure out why what I said was wrong initially is because this expected value, we take the expected value of random variables, because the expected value of constants are basically just constants. So it wouldn't make sense to say what is the expected value of, like, a number 2. The expected value of 5 is 5 no matter what you do with this 5, like it's going to remain fixed. So it makes no sense to say expected value of y if y is fixed. And that is the best way to, like, figure out if someone is saying something wrong. um Maybe I haven't spent enough time reviewing this. I think the understanding was to find this optima of, like, I guess, yeah, I don't remember why this middle term goes to 0. It's y minus expectation of y and expectation of y minus mu. Um, I suppose what they're trying to say is the best value for mu at which mu tends to 0, is this term. I get, oh, this term does not go to 0. What they were saying, Yeah, I'm really not sure. I will review this and get back on this on the group. But I think what the point of this is, once you get this equation, this whole equation for the mean squared error, you can just differentiate that with respect to m here and set that to 0 to obtain this. Set that to 0 to say that with respect to m, the minima occurs at this point. This is my optimal point forecast. And that gives me the value of this optimal point forecast being the expected value of y. I guess that's all that they were trying to say there, and I confused another explanation with this center term going to 0. So that's on me. Um, but if you substitute this back into this mean squared error, yeah, crap. That's what I missed. If you substitute this value back into the mean squared error, then you see that the center term goes to 0 and the last term also goes to 0. And that's sort of why that is your optimal value. All the terms that depend on mu go to 0. So essentially you've minimized all the error that you can. And that is why it is the optimal point forecast. So thank you again for bringing this up. And I'm a bit rusty because I taught this a long time back. But I should know all this. Anyway, hopefully that was clearer. And we can now jump into um, why is it, what time is it? My iPad says 9:41 a.m. Huh, interesting. Frozen in time. Um, okay. So we are at 20 minutes in, and I hope to complete this chapter in 45 minutes. Hmm. Okay, let's see. So we go on to like the next step where we want to estimate this expected value of y. Um, we do not know this, and the reason we do not know this is we don't have the entire random variable. We just have samples. And by samples, I mean you have some outcomes of some experiments. You have not run the experiment infinite times and gotten every possible value for the outcome. So just like in the real world, you can think of this as we do not have all the possible data. So what can we do? Well, take estimate the expectation using these samples by saying I take the average of this as the value of the random variable. And that leads you to this blue square, um, where you say that my estimate no mind where you can say that my estimate for this expected value is the sample mean. And there are certain subtleties where you cannot always just substitute the these things in and out. So you have to remember where you're using it, what you're using it. There is some bias that comes in, there is some variance you have to consider. So we will get into those details in the second chapter. But for now, it's an estimate of the sample mean. And as it turns out, the sample mean is an unbiased estimate of the mean. But again, we'll get into unbiasedness later, which is why I held off on that. It's just a way of saying what is the best you can do. This is the best you can do. Just take it and work with it. And it's this next point is pretty critical. This idea of independent and identically distributed samples. So what it's saying is, for data, um, there are two ways of selecting data. One is by saying that the data is not two ways, I guess there are more ways, but the idea of IID is like saying I have a bag of all of my data, and this bag is like a jute bag, and I'm picking random data points out of this bag without actually seeing what they are. And another way of picking data that is breaking this IID assumption would be to say, okay, now I have a plastic bag and I can actually see, and if my data are balls, then I can actually see the colors of these balls. and I'm looking at them and I'm picking the balls that I like. So it's not random. And that is a super critical assumption. And it's broken a lot of times in practice where you don't design experiments well and suddenly you don't have IID samples, but you still try to assume that they are, and then you end up with poorly fitted models as a result. But anyway, like this idea is hard to tie down, is important to tie down. So IID versus non-IID. And anytime you do something like this, like you take the sample mean, you're implicitly making this assumption of saying that, okay, my data are probably IID. So I can just average all of them and say, okay, on average, this is the value my random variable would take. Yeah, there is this law of large number that tells us as your data increases, as you get more and more and more data, your average will tend to this true expected value. Um, and one way of like why that is so important is because in a lot of applications you have a lot of data, and the fact that this more data you have, the better the representation, although super intuitive, is also super important in statistics, and we'll get into why. This law of large numbers, more complicated applications of this law of large numbers. Another thing is about the convergence of the squared error. And as you get more data, the n increases and your convergence, the squared error decreases. So, which is also pretty intuitive. Like the more relevant data you get, the lesser, the better your predictions will be. Um, I'll get into this uncorrelated but not independent point later. For now, let's move on really quickly to the regression function. So we have um, y, which is our dependent variable or output or response or regressand. And I know these are all annoying names to have to remember all the time, but trust me, if the more you talk about it, the easier it will be to remember. And the x's are called predictors, independent variables, covariates, inputs, or regressors. Again, it gets easier to remember after you use them for a while. So what we want to do is use our x's to predict our y's. That is our goal. We decided that y is a function of x. Our predictions will be a function of our x's, right? We didn't decide. I mean, we know. Um, and the mean squared error of this prediction will simply be the same form. So earlier we used y minus m the whole square. Now we replace m with function of x. We do the same analysis, and we obtain a similar result. Um, what else do I want to say about this? This uses something called the law of total expectations, and or the law of iterated expectations. Either way, like there is a proof for it that I've basically written down. I think I copied it over from Wikipedia or built it myself, but double check that it was correct. Um, the idea is, actually I should talk about conditioning. Um, so this vertical line basically is indicates that you condition one random variable on another. So what you're saying is, if I perform two sequential experiments and I pick only some values of the second experiment where I see some values of the first experiment, then that means that that second experiment, so if I flip, my first experiments is coin flips. If I flip heads, then I eat some chocolates, and if I flip tails, I don't. Then the number of chocolates I eat is a function of those heads. And if I take that expected value, it's not actually the expected value of the chocolates I eat. There is some effect that is affecting the second experiment, so I'm conditioning it on the outcomes of the first experiment, and you can imagine that to be more complicated as the number of outcomes increases for both. So that's this idea of conditioning. And what this law says is, if you the expected value of a conditional expectation, right, is equal to the expected value of this. y itself. And there is a proof for this, but the intuition is, um, you are averaging over all of the values of the first experiments, which basically renders it meaningless to actually perform the first experiment first and then perform the second experiment a lot of times. Um, yeah, I think that's all I want to say. So that is why this first term of iterated expectations is equal to the second one. But the advantage of that is sometimes you only see like this set of results in sequence. Sometimes you don't see all of the results of the second experiment. So at those times, it's helpful to cast this as conditional expectation, solve for that, and then go back and say that, okay, this is the same as the original. So yeah, I guess that's it. That's all I want to say about this. And from the previous proof, but like this using this law of total expectations, it is easy to see that this results in a variance and a bias squared term. And by it's equivalent to the conditional variance and conditional bias squared, I guess. um yeah, I don't think I want to say more about this unless someone has a doubt. Okay, so the with solving these equations we basically obtain this one, that says mu x is equal to expectation of y given x, which is the conditional mean. So the optimal prediction is the conditional expectation of your response given your covariates. And this is a pretty important result, because it is used in a lot of downstream applications. And remember that this conditional mean is not a constant. It is the expected value of a random variable given another random variable. So it will be a random variable. Um, uh, it will be a function, random. A function basically could describe how a random variable varies. Um, yeah, it's important to talk about some assumptions that we have made here. Um, or at least in this section, he just clarifies that just because y is a function of x does not mean x causes y. That's it. That's the takeaway here. So just because yellow teeth um, relates to lung cancer in some way does not mean lung cancer causes yellow teeth or that people with yellow teeth have lung cancer. Um, so, like, don't infer causality from correlation, is his point. Mm, in general, so this is a general way of formulating the problem where, so before we assumed y is equal to beta x plus epsilon, where epsilon was this noise term. And we say Gaussian noise, we say white noise, we say these things to basically imply that this is uncorrelated with x. So epsilon and, sorry, covariance of epsilon and x is 0. Okay. But this does in a this is an assumption. This assumption might not be true. So in general, your noise could be a function of x. So that's what he's trying to say, that it is always true that y given x is a function of x plus a noise which could also be a function of x. We assume that this is not in order to make our life easier, but it could just vary with x, and that makes our lives difficult, and that is actually chapter 10. So I will hold off on saying more than that right now. Um, Yeah, where epsilon is a random variable with expected value 0, but as the notation indicates, the distribution generally depends on x. It is also important to be clear that if we find the regression function is a constant, this does not mean that x and y are statistically independent. If they are independent, then the regression function is a constant, but do not turn this around. And there is a simple example to prove this rule that um, independence implies uncorrelatedness, but not vice versa. And the simple example is this: if you draw x from a normal distribution, which has a 0 mean and variance 1, and if you say y is equal to x squared, okay, by variance 1 and mean 0, we mean that expected value of x is equal to 0 and expected value of x minus expected value of x, the whole square, is equal to 1. This is the definition of the mean of the first and second moments respectively. In this case, we can substitute this is 0, so this boils down to expected value of x square. And we can prove that the covariance of x and y is equal to expected value of x minus times y minus expected value of y um, is equal to 0. But they are not independent because y is a function of x. So uncorrelatedness, which is covariance 0, does not imply independence. And that is the point that it resurfaces a lot of times in statistics. And on paper, it's easy to try and harp on this point, but in practice it is not the case. It's much harder to note this in practice, where we typically start inferring independence from uncorrelatedness, which means like when you perform all these tests of whether a consumer likes a particular product image on a page, and like your hypothesis tests, this comes in very crucially. So yeah, I just wanted to boil down that example. um what do I want to say about this? I guess not much, because what he's trying to go for now is like, so far we were talking about this x, which is a random variable, and y, which is a random variable. Now we get to estimating this x from your xi, which are your samples, and y from your yi, which are your samples. And when you start doing that, you introduce some errors in the process. So it's not straightforward to always say that okay, my samples will be perfect, because again, you have limited data, so you don't always know everything. And that's what he's trying to get at with the rest of the chapter. So one point he raises is any kind of function estimation from data points is going to involve joining those data points, removing noise and or smoothing. And when you try to do smoothing, you get into errors because you're making assumptions of what lies between two data points. um yeah, so this goes back to our bias variance trade-off. Hmm. Okay, so this goes back to our bias variance trade-off, so I'm not going to go back into this. um just note that it gives you a variance term and a bias squared term when you break it open. um You again talk about your noise being a random variable which is expectation 0 and is uncorrelated with x, which again deals with epsilon x in the general case. Under your assumption, this goes to epsilon which is uncorrelated with x. Um, what
Hello,
else?
Swapnil.
Yeah.
Sorry to interrupt you. Actually, I had a doubt in the estimation of regression function. So there's an equation with hash. So I don't know what that notation indicates
Oh, a
actually.
count.
Okay.
Mhm.
Okay. Thanks.
So 1 by the count of the number of samples. Let me double check. Conditional sample means 1 by I x is equal to x y I. Yeah, I believe that is it.
Okay. Thanks.
Okay. Um, so stepping back, like now we know that if we have an x and a y, we can make a particular prediction. Oh, there is a chat message. Oh, okay, that was you. Yeah, thanks. Please interrupt me because I might not notice the chat. And I always appreciate you interrupting me. As Kushal has proved, it really helps clarify things for everyone. So we got our bias variance decomposition with this particular equation, and with this particular task of minimizing the mean squared error, we could decompose the mean squared error into a bias term and a variance term. And our what we're now going for is like stepping one step beyond that. Like we've made some assumptions of a very simple case, but in reality, like our data are going to come from different sources. Our models are going to come from different sources. So like how do you tie this down in a more general sort of sense? What is the canonical way of thinking about this? So suppose we define like a set of estimators, um, and I haven't really harped on estimator, estimand, and all of that. um, I'm going to assume people know about estimator. I did speak about estimators. Okay. So the way we do this is that our data come from some data generating process. DGP gives us our data. So in a sense, our data are random. Like we sample these from this DGP. So that's what this point is trying to say. So because this data are random, the estimator, the estimate that we obtain of our true function, to be fair, this should go back up. You want to estimate the DGP, right? So the estimate you obtain of the DGP will also be based on these samples. It's a bad diagram. Will vary with the data. Yeah, that's all he's trying to say. And then he formalizes this with some mathematics, saying if we define this random function of m, capital M hat, um, as this regression function, which is random, um, then what we can do is say, okay, with respect to this function that represents this random variable that represents regression functions, what is the error and what is the expected value? um, and again, like we discussed, expected values are used to get summary statistics, so we want to know how it varies. And it's not easy to like describe it by taking individual values, so we just find these summary statistics to describe the behavior of this estimator. And now we want to average this over all possible training sets. So if you want to find the expected value of this estimate, you know that it varies with respect to the data. So you calculate the expected value with respect to the data. And you condition it. Sorry, my bad. because you say this varies with data. It depends on a particular value of x, which is why we consider this conditional distribution. This small x is called a realization of this capital X, which is a random variable. So realization of a random variable is what you condition it on. So in the coin flip experiment that we spoke of, the random variable is the outcome and the realization is either heads or tails. So that's what you condition this on. And going back to our law of total expectations, you can rewrite this as an iterated expectations. So you still keep this on the outside, and then inside you take both of these terms. So like they said, inside you can condition in on an extra term, and as long as you average out over that extra term, you're fine. And this internal expectation we have as the bias variance trade-off, right? So so we rewrite that as as the variance plus the bias squared, conditioned on this external x. And now this variance of the noise can come out, um, because for a particular the variance of the noise is fixed. That was our assumption that we made. And what remains inside is this bias squared term. And for this bias squared term, again, we do the same thing that we had done before. We add an expected value, subtract that expected value, and then we expand that out into another bias variance decomposition. So now this bias variance decomposition, so um, if there is a confusion, stop me here, because this is like a two-level bias variance decomposition. And instead of doing it for one data set, we are doing it for each data set and then averaging over all data sets in order to examine the behavior of this regression function, right? So a regression function examines the behavior of this particular model on this particular data set. What we're doing is stepping one step above, saying, okay, for all data sets, for all functions, what is this going to vary as? And so that is what we end up with. And
So
yeah,
just a question. So when we say that we are trying to approximate different regression functions for data sets, so how do these data points, so are we, so suppose we have a data set, and to estimate different regression functions, are we taking data points from all the data that we have available to us, or like do we create subsets from our available data points?
you can think of it in a way as creating subsets, but what he's going for is you draw samples from this data generating process. That's why this
Okay,
X,
okay,
capital X, is random,
okay, okay, cool.
right?
Thank you.
So at this, I could write this down. So our data generating process is P of X. Our data are, well, I should say our data are X, Y. Sorry. Um, I don't know where to move this. Okay, let's say X is equal to X, Y is equal to Y. And that is what, like, this estimate will be dependent on X is equal to X, but now we want to take the average, which is why we take the expected value over X. Cool. um oh, oops. um hmm. So what I'm questioning is they use this notation X throughout, um and this mean squared error is the value of this estimate at this particular X. So I guess they are fixing X, um and obtaining the behavior of the estimator on average. Oh, right. Yeah, yeah, yeah. Yeah, okay. No, my explanation was okay. The reason I'm saying is like taking the expected value of your estimators for not overall data sets, but over a sample of the data. Oh man, this, yeah, I guess really unprepared for this. Um, but okay, let's read through this. I'm concerned because there's this time pressure and I really want to get through 3 chapters, but it doesn't seem like that's going to happen today. Um, anyway, well, it's more important to like tie down these concepts. So like let's read through it and see what I said. Suppose the true regression function is mu of x, but we use the function mu hat to make our predictions. Let's look at the mean squared error at x is equal to x in a slightly different way than before. This will make it clearer what happens when we can't use mu to make predictions. We will, mu is the true regression function, right? Again, we will begin by expanding y minus mu hat of x the whole square. So this is the mean squared error at x is just the expectation of this. Okay, they expand the mean squared error, and this tells us that y minus x is equal to uncorrelated noise. That is true. So what remains after making your prediction is the noise. That is fine. And the mean squared error of this estimator give for this data set is equal to this blue line, which is also fine. Sigma squared term does not depend, it is the intrinsic noise variance, that is also fine. This is our first bias variance decomposition. We've done this before. All of this presumes that your mu hat, your estimator is a single fixed function. Really, of course, estimator is something we estimate from earlier data. But if those data are random, the regression function is random too, which is a function of this estimator. Um, yeah, I think what I said is correct. I just got confused by the notation. So this m hat of x is basically implying that it is a function of the data. Capital M hat subscript n of x is an estimator, which is a function of the data, which is what we said here, that your estimator will be a function of your data and you want to find on average how will it vary, which is why you break it down and arrive at this decomposition, which tells you for a particular x taking for the data taking a particular value of a realization, this is how the bias variance decomposition will break down. Okay. Please tell me if this is still unclear or if I spoke too fast. Okay. Um, I'm going to assume people followed. Um, but yeah, my explanation was right. My confidence was not high. Um, there is an important catch. And a lot of times, like in machine learning, they say this bias variance trade-off. But it is not necessary that it is equal. So it is possible that your bias can be reduced by more than your variance increases. So overall, your error, which is a combination of these two terms, bias plus variance, variance plus bias squared, your bias can be reduced by more. So your overall error can be decreased, but only up to a certain point. That is the meaning of this being a trade-off. It is not necessary if bias goes down by 5, variance will go up by 5. It can go up by just 3. So your overall error still decreases by 5 minus 3, which is 2. And that is like important to note. Now, I don't want to talk about consistent methods as much, but I can just read this out. A method is consistent when both of these, the bias and variance, go to 0 as n tends to infinity. That is, if we recover the true regression function as we get more and more data. Which sort of makes sense. Like as you get more data, you want to predict perfectly. Um, oh boy, now my battery is going to die. Just the perfect day. Um, oh, maybe I have an idea. Okay, at least the battery issue has been solved. How much time do we have? Exactly 1 hour. Hmm. Yeah, I guess I will refer you to like the video on chapter 3. I think there is one. But the audio is separate, so I don't. No, let's see. Let's see what we can do in 1 hour. I've taken a lot of time to explain these concepts, so I hope they are clear. What is this least squares? How is the bias variance trade-off obtained from this least squares estimation? What is this error minimization problem? And some stuff about this assumptions that we make. I will breeze through the rest fairly quickly because it is not as complicated. What he's saying is sometimes it's Occam's razor. Occam's razor is this idea of the simplest possible explanation is most likely the correct one. So if you have this true function, which is this black line, and you have some data drawn from it, and you want to estimate the function, it is often more meaningful to make this simple assumption of a straight line, which is this red line, this straight line, as opposed to trying to fit this complicated blue model to it, right? That is all this is saying. Even though this blue model has the right functional form, so like a plus b sine x, which is the true model, because this, if you set this a to what, um, hmm, sorry, this is your y. So if you set this a to 1 and you set this b to 0.01, you will actually obtain the true regression function, but you don't have enough data to do that. So in such cases, then in typically in real life, when you don't have enough data, and a very good question would be like, what is enough? And it varies by problem, but that is the general, in general, it is it might be more beneficial to make this assumption of the simplest possible model for the uh, example, as opposed to going to fit more complex models, because that red model leads to less error than blue model in this case. So it is actually a better model, even though it is not the true model, and it can never approximate the true model perfectly, because you cannot fit a straight line to a curvy line. Like you cannot find the parameters. This line, the best case will be this straight line. For the red line, if you try to fit it like perfectly with infinite data, that is the best case approximation you'll get. Whereas the blue line will actually go to this curve here, um, given an infinite data. But what the author is saying, that in real life you don't have infinite data, so this red line will never go there, and blue curve will never fit that. So just use the simplest possible assumptions you have. And I'm spending more time here because this is important. So this might be the bias of you sorry the bias of using the wrong functional form is less than the extra variance of estimation. So using the true model form hurts us. So the true model form, the blue line, has more variance. This red line has much less bias, um, which is why it works. Um, then he breaks down this, and this is fairly straightforward math, so I'm going to leave it to you. But he breaks down this regression form, um, which in terms of like this model, um, b naught plus b1x. So what is the error of y minus b naught plus b1x? And he breaks down that mean squared error in terms of, again, a variance and a bias squared term. So exercise read that, understand it, and arrive at this final equation where your prediction is a function of the expected value of expectations, variances, and covariances. And the reason this is nice is that now, because you have all of your data, your y and your x's, you can actually calculate this prediction at a given point, at a particular point x, by substituting all of those values. So this is mathematically solvable, and that is what we call, like, that is why we say that the linear regression has a closed form solution and neural networks do not. Like, there is, at least to my knowledge, you cannot mathematically solve a neural network because there is some randomness involved in that process, that you can't guess. Or I guess the ways that we solve the optimization procedures are stochastic. Um, yeah. Whereas there is a closed form solution possible in this case because there is no stochastic optimization going on. Stochastic basically means random. Um, yeah.
Hello, Swapnit.
Yeah.
In the derivation above, is B naught is beta not a derivative of B naught, or is it representing the same term, or are they both different things?
So
Yeah,
I
just about that.
so this one you're saying, right? I think what
Yeah.
they're saying is like B naught is this estimate of beta naught.
Okay.
Um, but I might be mistaken. So let me read that again. First term B naught B1. MSE of A comma B. So it's just a variable. Um, is B naught y minus B naught plus B1x. And then you find this optimal value of A naught and B naught, and you substitute beta naught and B1 for it. So beta naught and B1, beta 1 are the optimal values of B naught and B1, if I understand correctly.
Okay.
Mhm. Okay. Moving on. Once you find these optimal values of beta naught and beta 1, you can substitute them back into this equation. So your estimator you originally said was beta naught plus beta 1x, right? Or to be clear, you said, um, I'm going to assume y is equal to b naught plus b1 x, and then you find that b naught has this optimal value, or not the optimal value, but let's say that your estimate, which may or may not be the optimal value, that's the reason, that's the difference between estimate. It might be the optimal value, it might not. You say that I estimate this with beta naught and beta 1. So when I substitute it in my prediction, I have my data, x, and again, small x represents this realization, heads or tails, as opposed to the random variable x. So it's a fixed value. Your beta naught and beta 1 are fixed values. So that means you can obtain a value for your prediction at this point x. Hopefully that notation is clear. And what we are saying is now, substituting these two values um, back into this equation gives you this form where you are now weighting your terms. And by weighting, you mean you're calculating the distance from the mean and using the standard deviation. Um, so the point of this derivation is to try and arrive at a form that is intuitively understandable. It is still linear regression, it is still the same setting. It is just saying that, okay, if I define my y to be b naught plus b1x, then this is how I use my samples to obtain my predictions. So you're taking these two distances, um, which is averaging over a distance of all the points from the mean and that point from the mean, in order to obtain the prediction for that point. That is all that this is essentially telling you. So our prediction is a weighted average of the observed values yi of the regression, where the weights are proportional to how far xi and x both are from the center of the data. Right? That is the idea. Um, yeah, I'm not going to spend too much time on that. What I'm going to talk about now is more of linear smoothing, um, which estimates the function with a weighted average. So So we got to this point where we said that your prediction is essentially a weighted average of the data. And there are different ways in which we can take these weighted averages, which is what gets us to this idea of nearest neighbor regression. So what if I have points like this, and I don't want to use all the points to make a prediction at this one point in red, or sorry, at this one point in red. So you have an X and you want to make a prediction of where your Y will lie along this red line. And you want to use the points that are close to it and not these points. So one way of doing that is just to reduce these weights to 0. Whereas these weights are all, because these are 2 points, you allocate this half the weight and this half the weight. So essentially what you can generalize to is saying, if I have k nearest points, I can pick k nearest points and give them each weight 1 by k. And to rest, I give weight 0. So I'm only using these close by points to make my prediction at this new point x. And that's it. That's k nearest neighbors. The second point is, and I would encourage you to read through this because he raises a lot of points. So like I've highlighted and given you good notes, just read through them later. I'm skipping through them faster right now in the interest of time. So changing k lets us change how much smoothing we are doing, but it's a bit awkward to express this in terms of data points. So you, at the end of the day, like you don't know always what the right k is going to be. You want to figure out what this k is. And that brings us to this idea of kernels. So what kernel regression does is, same problem, we have all of these different points. Now, instead of saying I will pick these 3 and give 1 by k, I say I will pick all of them, but the probabilities that I will give them is varying with the weights that I will give them is the varying with a certain distribution. So what I'm saying is, if my data, let me draw this with a different color. Um, if my data distance, so if this is my x, so if I want to make a new prediction at this x, then my weights will vary with distance. I should, this is my 0 on the x-axis. This is my y-axis. I should not write x and y because that is my random variable also. So I'm going to say my weight varies with distance. So if this distance is 5 units, then I will go here, um, um, go to 5 units and see how much weight on the y-axis do I have to give it. So this says weight 1. Wait, well, let's not say 1. This is 1. Um, whatever that this, let's say 0.3. Then I give it at a distance of 5 units on both sides. I give it a weight of 0.3. And that is the idea. So at for any point, if I want to find the weight of this point, I calculate the distance from the new point, 6 units. I go to 6 units and give it the weight 0.1 corresponding to whatever this value of 6 units is. So this function here, I call my kernel. Yikes. And the idea of kernel regression is to place such kernels on your data such that no point has zero weight. So this kernel extends to infinity. Like even a point at infinite distance will have some weight, very, very, very low weight, but some weight. And then you can define different kernels. Like your simplest kernel could be something like a fixed value. So a box kernel at this interval and zero everywhere else, right? So something like this. Um, and you're saying basically if I have k by 2 on this side and k by 2 on this side, then this reduces to your k nearest neighbors because you're placing the same weight 1 by k at all of these points that are at up to a distance k by 2 minus k by 2 to k by 2. So like that's the idea. um so this is a more general case where you can also reduce to k nearest neighbors, but you don't have to, and that gives you slightly better estimates. um Based on this gets into the idea of smoothing, of how much you want to smooth your data. And if you don't smooth it a lot, you arrive at this red curve, which is very wavy and tries to fit everything. And if you try to smooth it more, then it tries to pick more data points to pass that line through. And by definition, that turns into a more smoother curve. So yeah, that's for k nearest neighbors, um, and which is like a special case of this kernel idea. There are certain properties that you have to pick for your kernel. Um, with zero mean finite variance. But again, like you can go through the details at a later point. Um, you have to remember that this weights have to sum to one, because like otherwise it makes no sense, right? You have to normalize how much you're using to predict your point. Um, I don't think I want to say anything more about that. Hmm. Yeah, I don't think I want to say anything more about that. So choice of kernel varies. And as your kernels vary, so do your estimators. There is some analysis of like how a particular case of a kernel. So you know that this normal distribution, normal with mean mu and variance sigma, can be written as 1 by root over 2 pi epsilon not, oh sorry, 2 pi sigma squared exponent minus half x minus mu whole squared by sigma squared. And then it tries to figure out like, okay, if this is my kernel function for this x given a certain mean and variance, then if I have a particular point xj and xi and my original point x, not original point, but like what it's trying to say is, in order to make a prediction at x, what will be the contribution of xi and xj? That's all. Like that, there is this nice analysis that I would encourage you to read. um, but the general idea is just further away you go, the less weight you want to give it. Nothing more. Some general theory for linear smoothers. Again, not not something that's ununderstandable, except for this idea of influence matrix or hat matrix. So now we are getting into this idea of figuring out um, this concept of degrees of freedom. So the geometric perspective on linear regression, or which involves a bunch of linear algebra. I wanted to walk you through all of it, but I clearly didn't estimate time well enough. Still, I will try my best. Um, Suppose that y is equal to mu x plus epsilon. Suppose, and just assume that that is actually the case, right? Now we define this smoothing matrix, um, which is essentially this matrix W that we can multiply with x to obtain y. I don't know where they had written this, but so this is what we can assume. Um, yeah, I don't think there's anything more to it here. But now what we want to do is, assuming that this is the case, so that your prediction is going to be W times Y. Now this is in terms of its individual components. So you index from j is equal to 1 to n. And if you solve for that, your goal is to understand the variance of this estimator. And for those who are concerned about the bias is 0 because um, expected value, if you expand this out, you will obtain, well, I'm not going into this. It's a one-liner. Hopefully it will be clear. If it's not, ping on the group and ask me, but read about it. It's already mentioned 3 times, so you should be able to know. Anyway, that's why we want to analyze the variance, and we obtain this equation for the variance. Um, you use this assumption that the noise is uncorrelated and the noise variance is constant. Again, we will get to particular chapters where this breaks. But again, the high level idea is, okay, we define this influence matrix, and why does this influence matrix matter? Well, it matters because this influence matrix can tell us about the degrees of freedom. I spoke about the closed form solution. Um, and by that I mean this, like when you have a particular set of data x comma y, um, x I y I, where I goes from 1 to n. I should write this here. Then we can use this data to actually estimate the least squares coefficients beta hat, through this equation, x transpose x inverse x transpose y. So we have a matrix of x's and y's, and we can fit this estimator to using this closed form solution. And if it's not clear, and I've mentioned this before, Carlos Fernandez Granda has some very nice notes. It's called Probability and Stats for Data Science. It's available for free on his website. Please look it up and read those notes if you want to see how you got the solution exactly. Um, but yeah, I'm not going to go into those details right now. So your W, which is your hat matrix, is essentially this entire thing, this x times x transpose x inverse x transpose. And what we're going to do is analyze the behavior of this W to sort of reveal more about what is the influence of each y on the prediction. So what we want to do is analyze how the response affects our predictions, and that's why this is called this influence matrix. um yeah, so notice that W depends only on the x's firstly. Yeah. If we change around y, the fitted values will also change, but only within the limits allowed by W. Sorry, is there a question? Okay, I'm going to assume not. um so again, this assumes a bunch of linear algebra background. but I've tried to give you like a lot of context on the side. So if you read these notes, I will share these again, in case you don't have the shared Google Drive folder. But I made some updates anyway. And yeah, I keep hearing someone, but maybe not. So what it's trying to say is W has to vary on a p-dimensional space within the this n-dimensional space of x's and y's. And this idea of residuals that it assumes you know, but residuals are basically what remains after you subtract your predictions from your true from your response. So what's remaining are your residuals. That's this idea. um or in this case I guess you would say y minus x. No, bad. Yeah, x beta is the right way to say it because we've been working with beta so far. So that those are your residuals. Anyway, what it's geometric, it's trying to use some matrix algebra to explain to you that this subspace is this rank of the matrix, and because this W is an idempotent matrix, and if anyone remembers what an idempotent matrix, if anyone doesn't remember what an idempotent matrix is, it is a matrix where A transpose is equal to 1, I think, or I to be precise. So A transpose is equal to A inverse. Does it? I think so.
That's orthogonal
Yeah.
matrix.
Yeah. I thought I also wrote about it, but okay. Anyway, so because of these properties, we use this trace of the matrix to define this rank, which tells us about the degrees of freedom. So trace to rank to degrees of freedom. And we can use certain algebraic matrix properties to show that this degrees of freedom of your estimate is really just a trace of your matrix W. Where again, W was the hat matrix, influence matrix that tells you about how much influence each individual Y had on your estimator. So yeah, and in the case of this linear regression, this trace is just equal to P, the subdimensional subspace within your n-dimensional space. Because of the way we structure the problem, it only has the freedom to move about a p-dimensional subspace. And I don't think anything else is necessary in this chapter. It's, oops, there is something. Um, Prediction errors. So there is a detailed mathematical analysis of this bias and variance of using this W to predict in your estimator. I am not going to go into too much detail because yeah, this is that, like, the math is not complicated. It just requires you to look up these concepts from either Carlos's notes or like the internet. Um, so Carlos's other course called Math Tools for Data Science also has good linear regression notes. I will link to it also. The key takeaway that I want to talk about here is if you use your WY as your estimator, which allows you to get to this bias variance trade-off again. Um, yeah, I don't want to say anything more about that. It's just arriving using the bias variance trade-off to analyze the behavior of this estimator. Particularly what you want to understand is the in-sample mean squared error. Now, what do I mean by in-sample mean squared error? You have certain samples. Your in-sample error is basically the error on your training data. And what you want this to represent is the error on your test data, which will only happen if your training data is well representative of your actual test data. Um, which I thought he gets into this here, but maybe it's the next chapter. Inferential statistics are, again, the towards the end of the chapter here, but the idea is ways of analyzing your estimators. um Not, I mean, it's not covered anywhere in this textbook, so you probably have to read it from elsewhere. But the idea is you want to be able to tell the user something about the uncertainty about your estimates. Like, if you repeat this process, and one way you can do that is if you repeat the process with the same data in like a shuffled manner, in a slightly different manner, like, will you arrive at the same results? Just minor perturbations to your data, to your process, whatever, and then will you arrive at the same? So all of these tests are in order to do that. They just tell you how stable your estimates are. um, Significance and hypothesis testing is in the next chapter. So have 25 minutes. I don't think that's enough for chapter 2, but I will try regardless. Still, I want to pause and ask about questions in chapter 1. Okay. Um, Seeing none, you can also, and I would encourage you to post on the chat during the week, because that we have more time then to discuss all of this stuff. Chapter 2 is about mathematical analysis of all these assumptions we make, and all of the teachings that not the teachings, but like the inference we can do using linear regressions. Like, what does a linear regression tell us, but most importantly, what does it not tell us? So that is what this chapter is about. um, we discussed optimal linear prediction with a single variable, but what if we have a matrix of, like, what if X is a matrix? And to some extent we did talk about that, but now explicitly we have like a p-dimensional X, p-dimensional vector of predictor variables. And we again arrive at this, we let's try to use a linear function of X, which is beta naught plus beta X. This is not an assumption about the world, but rather a decision on our part. This decision could be good or could be bad. Um, Again, like, the motivation is this graph that we spoke about, where you had a green curvy line, where you had a real line. Uh, yeah, the motivation is this, that even like complicated cases, your linear models might give you good approximations. So that's why you want to start with the assumption of a linear model and then see if that actually works for you. Ugh, I should not change pages. Okay. So that's why linear regression, we work with that. We saw that the optimal predictor is basically the conditional mean, expectation of y given x, which is a function, not a constant. Um, let's say we want to, and now we rely on this idea of this, that there is some structure in the world that we want to discover. So there is some smoothness that we want to uncover. If there is, if the actual data generating process has no structure, it's completely random, then we can't create any structure out of it. And whatever structure we create, no matter how we fit it, it will be bad because the true process has no structure. So we work with this assumption of there being structure, which means points that are closer together will can be connected by smoother lines than points that are farther apart. So there is some local sense of smoothness, which is what allows us to approximate points that, like, near the very close to a point, we can say that a line is generally Taylor expandable. And that Taylor expandable basically means it's this way of expanding a function about a point that allows you to take the derivatives and define that near these points this is the function. So, like, where did I go? Yeah, as opposed to saying this point will fit into this big function, we just want to say that roughly in the vicinity of this point, the function will be something like that. That's all we want to say. And even if it is something like that, something like that, it's still like an okayish approximation as long as we don't try to say it's going like that. And that is this idea of Taylor expansion, that within the vicinity of a particular point x, you can expand it and write it in such a way. Um, anyway, I see a couple of chat messages. Sorry, I missed those. Idempotent. Okay, great. Thanks. Um, whatever reason we want to use a linear function for, there are many linear functions. We can just pick one of them. We may as well do that by minimizing the mean squared error again. We arrive at this, like the two values of beta that we found, beta 1, beta naught. And now we write V as the covariance matrix of X. So because X is a vector now, we can't just write variance of X. We now have to write sigma as the covariance matrix of X, which is also, you can say, XX transpose tends to this sigma as long as you have a large number of samples. But we'll get to that later, by the end of the page actually. Yeah. So we get this same sort of decomposition for what I mean is we get the same equation as we got before, except now it's in a matrix form. Yeah. These conclusions hold without assuming anything at all about the true regression function, about the distributions of x, of y given x, or y minus mu x. In particular, nothing needs to be Gaussian, or whether data points are independent or not. So that is a crucial point. Like, this works without assumptions, which is also why like linear regression is so widely used, because it doesn't have to make any of these assumptions to arrive at this estimates for these parameters. The fact that we make assumptions relates more to where we know the data can have a particular structure and we want to approximate that structure. So that's where we start making assumptions. But when we have nothing, when someone gives you data from an unknown process, it's best to not make assumptions about it. What he says is this multiple regression, in the sense X comprises of these P columns of data, right? It could be simpler if we could just take each column at a time and then do regression with the Y and obtain the estimate for this parameters beta naught, beta 1, beta 2, beta P minus 1. It would be so nice if we could do that. And in fact, that is actually what is happening. So this structure of the variance covariance matrix for beta, what it's doing is essentially, if you decompose this into what actually I thought I wrote something down here. What is a matrix and what? Weird. A matrix is essentially like a transformation. So if you multiply something by a matrix, you're transforming that original matrix or whatever your original data is into this projection and translation operation, using this particular, defined by this particular matrix. So a matrix is an operator. And what you're saying is this V inverse is a matrix, so it is also an operator. So you can think of this multiplication by V inverse as decorrelating your X, applying a linear transformation to come up with a new set of inputs which are uncorrelated with each other. So that is what an interpretation of this could look like. And the clear problem that arises is, what if this covariance matrix V inverse, the inverse covariance matrix, it does not exist, like the matrix is not invertible. This will happen if and only if, and this again goes back to linear algebra, where the predictor variables are linearly dependent on each other. And I've given an example here where one column is just a linear combination of the other column, and that is not cool. That means this matrix is not invertible, and if you try to invert, you'll get a divide by zero error. In another matrix algebraic sense, there is at least one eigenvalue which is exactly zero. So I wrote a bit about eigen decomposition before. Read about what it means. Technically, eigen decomposition is basically saying if a matrix is a projection, then can we decompose it? And in a large number of cases, the answer is yes. So you can decompose it into this. Um, so I assume you guys are familiar with Cartesian geometry. So your I cap, j cap, k cap. Well, the equivalent in matrix notation is your eigenvectors. So your this matrix comprises of three vectors, one of which is a linear combination of the other. So if I say this is A, this is B, and this is C, then C is equal to 2 times A, right? Um, and like translating the same to like matrix decomposition, what we are saying is a matrix can comprise of this A vector, C vector, D vector, E vector, where all of these are orthogonal. So A dot C is equal to 0. A dot E is equal to 0 and D dot E is equal to 0. And so this is the same as saying your I cap times J cap is equal to 0. I cap times I cap is equal to 1. And the same thing holds here. A dot A is equal to I. So um, um, that is how like we decompose. So if I call this matrix U, like the basis matrix, then I can decompose any matrix A as its particular basis matrix Q, which is of this form U, by which I mean like it is a certain basis. So now the reason I say Q and U is because I cap, J cap, and K cap are along X, Y, Z axis. But here we don't have particular axis. We have an n-dimensional space. As long as your matrix is n cross n, right? P-dimensional. I should say p-dimensional space. So I have a p-dimensional space as long as your matrix is p cross. Shouldn't it be n cross p, p cross p, p cross n, so that you get n cross n? I think so. Let's simpler version, d-dimensional space. I'm just trying to explain this decomposition and like the geometric interpretation, right? So this d-dimensional space, it has a basis in this d-dimensional space. So Q has a basis in this d-dimensional space, and we can say A is equal to Q times a matrix lambda times Q inverse. And as long as this A is under certain conditions on this A, every matrix belonging to that class of matrices is decomposable in this form of Q dash. Like for their own matrices, they have Q dash, lambda dash, Q dash inverse. So like the idea is there will be this form where lambda is a diagonal matrix, which comprises of the diagonals called eigenvalues. Remember that a diagonal matrix was zeros everywhere except for the diagonals. And Q inverse is again orthogonal. Like we said, Q was orthogonal, which means Q transpose is equal to Q inverse. And Q transpose is equal to 1 I. So again, this is not an easy concept to understand in 5 minutes, but the idea was like similar to a geometric decomposition of a vector. You can geometrically decompose a matrix. It has a particular basis in its own dimensions defined by how big the matrix is. It has some values, some scaling factors. So like you say your vector a vector is equal to 3 I cap plus 4 j cap. This 3 and this 4 are basically scaling factors, right? So similarly, this
Hello.
lambda, yeah.
You said the eigenvectors will be always orthogonal. This will only be the case when A is symmetric, right?
Yeah, so under certain conditions on A,
Yeah.
You can decompose such that it follows this form. Those conditions are super important. I'm not saying real symmetric, mainly because I don't want to get into more details, but I guess it's simple enough. You guys understand real and symmetric matrix. Um,
Yeah.
so as long as A is real symmetric, you can decompose it in this way. Thank you for bringing that up. So hopefully that gives you a picture of this eigen decomposition, eigenvalues, and when this doesn't work, when this does work. And that's about it for that stuff. What do I want to say? So you want to the underscoring point for that section was that there are ways of dealing with this collinearity in your data. So what when you have collinearity, you cannot decompose all of this. So what do you do then? One is get a different data set where the regress are no longer collinear. Second is identify those variables and drop it from the data set. And the third is we could appeal to some extra principle that automatically handles these things. And that idea gets to regularization, but like in a more intuitive way. So you can also imagine this gets much harder in higher dimensions where you can't directly look at these matrices and compare columns and figure out which ones are correlated. Um, but anyway, we'll get to that. How are we doing on time? About 10 minutes left. Okay, fine. I will pause here for questions because it's yeah, it's not enough time to cover the chapter. Also we should figure out a time during the week because the challenge is like there are folks who are on chapter 10 and I don't want them to wait for like 8 more weeks for us to cover the rest. Or alternatively, we should organize like watching sessions for at least like the chapters whose videos are online so that people can watch them together. I can sit and like watch it with you. If you have doubts, we can pause and do all of that, but that also avoids this issue of me forgetting what the explanation was and someone having to correct me, which I really appreciate, to get to like in your interest. So yeah, questions and like I guess we should discuss this on the group, but are you guys comfortable with like organizing a couple of watch parties during the week? You can unmute and answer, you can raise hand, you can type on chat. I now have chat, but let me pause the recording.